I finally decided on a permanent employee wages, which are randomly assigned using a distribution below. So you're still drawing out of a bag. Additionally, at the end of every year, she gives her employees an hourly raise. Bonuses are assigned randomly according to the probability distribution of Y, which is on number 2. And we're going to assume that X and Y are independent because they are randomly selected, okay? That is an important piece that we'll come back to in a second. So, let's see if you remember. We want to find the wages, or the mean, and the variance and the standard deviation of the wages of X, that X table. Remember how we did that? How did we find mean? We used our calculators, right? So let's put this in our calculators. Yes. Oops. Stat, edit. All right. If you're like me, I got stuff in my list, so I need to clear my list. And then put in my new values are 9, 12, and 15. Okay. Once they're in the list, where do we go? Good, yep. Stat, calc, one variable statistics, but we got to make sure we put in list 2 as our frequency list. Boop, hit enter. And I found the mean to be 11.85. And the standard deviation is 2.22. Now, do you remember what variance is? Good, yeah. Variance is just the standard deviation squared. All right, so it's 2.22 squared, 4.93. Oops. All right, so that's for the distribution of X. That is your basic hourly wage distribution. And then the next distribution is the raise that you could get randomly. So this goes back to our list. We're going to enter this in our list. Y'all need another second? No? You okay? Stat, edit. All right. Now I only have a $1 raise or a $3 raise, right? And this would be a 70% of the employees will get a $1 raise and a 30% of the employees will get a $3 raise, right? Same song, second verse. So the mean is $1.60 of a raise. The standard deviation is 92 cents. So variance is my standard deviation squared. 0.92 squared. Oops, that's not squared. 0.84 or 85, sorry. Okay. Alrighty. Are we good here? So far, so good? Let's just review, right? Standard deviation, variance, means. We're all using our calculators, lists, and all that stuff. All right, great. Now, number 3 says, N is the new hourly wage for the upcoming year, which would be the result if I take distribution X plus distribution Y. Old salary plus your raise, right? So the first thing we need to do is look at what are all the possible hourly wages for the new year. Okay, so let's think about it. Let's say you had a $9 salary and you got a $1 raise. That means your new salary would be what? 10. A $9 salary, you got the $3 raise would mean your new salary is 12. All right. So I've considered both options of my raise if I have $9. Now let's do it for 12. If I had $12 and I got a $1 raise, it's now 13. $12 then got a $15 raise. It's now a $15 raise. A $3 raise gives me 15. right? Say it right. 12 plus 3 is 15. All right. $15, you get your $1 raise. I have a 16. And $15 plus 3 gives me 18. Now, what is the probability of an employee being assigned a $9 wage and a $1 raise? Say that. Okay, so probability that I had $9 and I get the $1 raise. Now remember, this is where we said earlier, these two events are independent. What you got for your first salary does not affect what you drew for your raise, right? How do we find an and probability when they're independent? Do you remember that? Somebody said it. What'd you say? You just multiply them. You just multiply them. So probability of a $9 raise was what, 30.3? So that would be 0.3 times a $1 raise is 0.7. Gives me a probability of 0.21. Now, we're going to complete that table. So we said if we get a $10, we just found this probability is 0.21, right? So we're going to do the same thing for all these other outcomes that we just had. We're taking these outcomes and we're putting them right here. 13, 15, 16, 18. So all I have to do is multiply the probabilities. For 12, it would have been 0.45 times 0.7, right? No, it should be 0.3 times 0.3, right? Huh?
Isn't that number supposed to be $9 and a $3 raise?
Yes.
Yeah.
So it would be, this one would be probability of 0.3 times 0.3, right?
Mm-hmm.
Which would give me 0.09?
Yeah.
Okay, and then how do I get 13? Well, that would be, my original was 0.45, the $12 times 0.7. Can't do that one in my head. .32. $15 then would be 0.45 times 0.3. 0.14. 16 would then be 0.25 times 0.7. And then this one would be 0.25 times 0.3. All right. Everybody see how we got those? How we combined them? Two events are independent. I can just multiply. Get that new probability. Now we're going to go back to our table, enter this new table into list 1 and list 2, and see what the mean, the variance, and the standard deviation is of this combination. Okay, stat calc. $13.49 Standard deviation is 2.41. All right, we okay? It's a lot of like keystrokes here, right? So let's zoom out and see what is this relationship. So if I'm looking at this, the mean of my combination, how does it compare to the original mean of x and the mean of y? What do you notice? It's them straight up added together, right? Just like it says, x plus y. 11.85 cents or $11.85 plus $1.60 gives me roughly $13.49. The rounding is a little weird, but it's pretty much the same. Does that make sense? Yeah, it comes 13.45, but it's just because the way we rounded. All right, but it is just the addition of this plus this, right? Now, variances. Look at the variances. We haven't had to do this before. Can we say the same about variances? Is 4.3 plus 85 cents roughly 581? Let's see. 4.93 plus 85 cents is 578, but that's just because we rounded. We're pretty much the same. Are we okay? So the variances are just added as well. Does it work for standard deviation? Not even close, is it? So what can we say? We cannot add our standard deviations. We can add the means. We can add the variances, but we cannot add standard deviations. So let's find a workaround, all right? So if that's true, how can we summarize that? We can say if n is equal to event x plus y, the mean of n is the mean of x plus the mean of y. Right? Now, we said the same thing works with variances, didn't we? So let's just do variances over here. The variances of x plus y, or I guess it should say n. We named it n. Is the variance of x plus the variance of y, right? We saw that that worked, but it doesn't work for standard deviations. But what could we do to this guy to get it to a standard deviation? Just take the square root, exactly. All right. We just have to add the variances first, then take the square root. We call this the Pythagorean theorem of statistics because they have to all be squared, right? But it has to be the variances squared. And I will tell you this. Okay, so everything was nice and easy, plus and plus, right? X plus y. If for some reason you ran into a scenario where it was, what's the standard deviation of x minus y? Guess what? This does not change. The variance of x plus the variance of y squared. It's always a plus sign right here. Even if the two things are being subtracted, it's always a plus sign in there. Okay? Just like Pythagorean theorem is always a plus sign. All right? Now, let's see if we can apply this to what we just, something else. Y'all ready to switch? Adding and subtracting the random variables x and y. So we just saw that if we add two events, we can just add the means, right? So it'd be just the mean of x plus the mean of y. If the problem is asking me the difference of two events, then the means follow suit. It would be the mean of x minus the mean of y. Those will follow. If it's subtraction, you subtract. But the standard deviations are special. Has to be in variance form. It's going to be the square root of the variance of x plus the variance of y with a plus sign. And if it's a difference, it's still the same. All right, so they're kind of special. Why would you need this? Well, sometimes you're going to run into questions where they have two events. They want you to combine them, and then they want you to find the probability using norm CDF. But you have to have the new mean and the new standard deviation to do that. But once you've combined all of that stuff, you're still using the z-score. It's still going to be, x minus the new mean divided by the new standard deviation, just exactly like what we've been doing. And then we would use norm CDF. All right, this is where the practice comes in. We'll have to do a lot of practice on this. You got to do the work of the combination appropriately for mean standard deviation and then apply it to the normal curve where you shade and find the probability. Okay, so let's look at this example. Let's try this one. Mrs. Chavez recently had twins. X is the number of diaper changes per day for Alice. Y is the number of diaper changes for Jocelyn. Based on a few weeks of careful records, the probability distributions of x and y are as follows. All right. So x is Elise, y is Jocelyn. So I'm just going to write that down. I spelled that wrong. How to do that? All right, diaper changes. All right. So there's the mean and the standard deviation of Elise's diaper changes and Jocelyn's. You can see them there. Define t as x plus y. Assume that x and y are independent. They have to be dependent for all this to work. You can't do that standard deviation thing if the events are not independent. All right, find and interpret mu of t. Well, mu of t is going to be the mu of x plus the mu of y, which would be 4.75 plus 4.9. Sorry, gives me 9.65. So this what gives us the total number of diapers? Okay, so we would say if we select many, many days the number of diapers used is 9.65. Now, can you use 0.65 of a diaper? No, but since it's a calculation, we leave it in decimal form. Okay. Now we're going to do the same thing, but this time we're going to find the standard deviation of the total number of diapers. Standard deviation of the diapers would be the variance of x plus the variance of y. So we got to do a little crunching here. 0.9698 squared plus 0.768 squared, and then we got to square root it. $1.038. But then we got to interpret, right? Remember what the key phrase is for standard deviation interpretations? Typically varies from what? The mean. Yes, 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 yes. Okay, so let's put some context. The number of diapers in a day typically varies by 1.038 from the mean of 9.65. All right. So all that's today's stuff. Part C is going to combine last week's stuff with today's stuff. Because you know they like to do that, right? They like to combine everything. So let's look at it. It says, Elise wears a diaper size 1, which is basically 20.238 of a dollar per diaper. Jocelyn has to wear size 2, which is 0.2975 per diaper. Find the mean and the standard deviation of the total diaper cost. All right. So if I was just looking at one of these babies and trying to figure out what is the average cost, what would I have to do with that price per diaper? Just multiply it by the mean, right? Would I multiply by the standard deviation also? To find the new standard deviation of the cost? Remember if standard deviation is affected by multiplication? It is, right? So I would have to multiply the mean and the standard deviation of diaper 1, or Alice's diapers, by this cost, right? To find my new, is that with me? Okay, so let's do that. So what do we say? So we're going to call this C. The mean of C, the average cost of all said diapers. All right, Elise has 4.75 diapers in a day at 0.238 of a dollar. That would give me the mean for Elise. Then I need to do the same thing for Jocelyn. Her average number of diapers is 4.9, but hers costs slightly more. That gives me 2.59 per day. We good? All right, now to find our standard deviation of a cost, you got to put your thinking caps on here. We know we're going to take the square root of something, right? How would I find the new standard deviation of the cost for Elise? How would I do that? Yep, just multiply the original standard deviation times the cost. So 0.698 times 0.238. Now, can I just leave it like that? This is standard deviation, so I've got to find that product and then square it to make it the variance. I know it's a lot, but you do the multiplication first because you need the new standard deviation to square, right? So give yourself that thought time to do it. And then we're going to do the same thing for Jocelyn. She is 0.768 times gonna have to square that and then add the variances, then take the square root. And I get 0.28, so 28 cents per day. Okay, so it's the variances that give students issue. All right, the means are not hard because it follows your logic. If you add, you add. You subtract, you subtract. Variant, standard deviation, you got to do a little extra, right? You've got to put it in variance form. You have to consider, is anything being changed about it, like added, subtracted, multiplied, divided? Got to do all that business. So